All right, welcome back. Now you'll notice I made a few quick changes. One is I moved this a little bit wider here so I can just see more of the code. And I also zoomed in, which you can control with the plus minus in Robot Mesh Studio. And I also zoomed in to take a look at the robot. So we can see here that our robot here has two motors and a sensor. And that is going to be used to control all the behavior that we use. Now, when you create objects in the Mimic system that Robot Mesh has, it automatically starts adding them to your kind of list of different motors and sensors. But if you were to build this yourself, you might actually have to go in and add them in the correct port. So this is saying that left motor is in port 2, right motor is in port 3, and then the bumper switch is actually in port A, which is for analog and digital sensors. So that gives us our basic understanding here. But what happens is how does it get translated into code? Well, if you see on the left-hand side, we actually have kind of an equivalency here. On the left, we have the brain, which is this guy. Then we have our two motors, left motor and right motor, and then we have the bumper. And these automatically got created when we started the project. Now, the left motor and right motor are both objects of the type motor. And the bumper, the push button switch, is an object of the type bumper. The brain is an object of type brain. Whenever you create something like a variable, basically you have to define a type. It has to have some kind of type. And so these are automatically created as motor types, which means that C++ knows that motors behave in certain ways. They have certain rules. In this case, in order to create a motor, you have to give it a port, you have to give it a gear ratio, and you have to tell whether it's positive or negative value. So in this case, I actually inverted the polarity. So that means that's the difference here with the false, and that's why one is false and one is true. So basically, how this is set up, the left motor and right motor, you tell them both to go forward, and it will work properly, even though one motor is actually flipped upside down. That's what that is. So basically, when these are defined, we are giving it some values, which we can then are used to actually fully define this object, which is great because then that means that we can do all sorts of great stuff with it. Now, once we understand what these things are and how they're created, you don't really have to worry too much about it at this point. Just trust that Vex is kind of looking after itself here. Inside here is our main program. This is what actually executes when you press run. Right now, nothing is going to happen. But we can quickly make something happen really easily. So the easiest code that we could give to a motor is to tell it to spin. So we say left motor dot spin. And then you'll notice that there's like a tooltip that pops up with suggestions. And there are lots of different options for spin. And I'm actually going to make this even bigger and so that you can see the different options. So if you press the brackets, you can see that I could just give it direction, or I could give it direction and velocity units, or direction, velocity, and percent units, or direction, voltage, and voltage units. So what I could do, the easiest one would probably be, the one that gives me the most control would probably be the spin with the direction and velocity and percent. So what we're going to do is we're going to go vex and then colon, direction type, colon, and then we choose forward, then a comma, and then the velocity, which actually does not need to be very high, 30, and then we go vex, colon, percent units, colon, percent. Now, we can actually, for Robot Mesh Studio, we should be able to just get rid of this part and just pass in forward like this and % like this without having to type in the whole long thing. But basically, this is where it's coming from, is like a what's called it's an enum from the Vex library. But we don't have to, hopefully it's actually been added properly and we don't have to do it. So we just type that. Next, we go in here and we type in, I just copied it, I'm going to paste it again, and we're going to do rate motor. Same thing. And we tell it to go forward because the polarity is reversed, which means that it'll just make it go forward normally. And then, now if we run this code just as it is, it's not going to do anything because we also have to give it a sleep. So we tell it to sleep for a certain amount of time, and let's say 3 seconds. So it's going to drive forward for 3 seconds. And then the problem is, even after sleeping, it will actually still go, but the code will stop, which means it'll unexecute. But if you wanted to have other code, you're going to actually have to have a stop of some kind. So let's tell them to stop. So left motor dot stop, and then right motor dot stop. And we're not going to pass anything in right now, but we'll talk about like different types of stops in a bit. For now, we're just going to tell it to stop. And let's see what happens. So in theory, we should be able to move for 3 seconds. It's probably going to touch the wall for a while, so why don't we actually say just 1 second? It's going to hit, otherwise it's going to hit the wall. We don't want that. So let's press run. It's going to fall and go forward for 1 second. That's it. You'll notice that it started to drift after, so it's actually drifting forward a little bit. And to avoid that drift, we actually can set different types of stopping types. So at the beginning of our code, we can actually go left motor dot set stopping, and we can choose, and we can see the different options. So Vex, : break type, : and we have a few: coast, break, hold, undefined. So break means that it will stop it when you press stop. It'll actually apply a brake, but then it's not going to actually do any work on the motor after the velocity has gone to 0. Hold means that it'll apply the brake, and it'll also try to keep it at that position even if there's any sort of resistance or push. Coast means that it actually is not going to do anything after it just turns off the motor, but any momentum that was built into the motor will still happen. So brake is fine for our purposes. Hold is something that you would probably use for a lift arm or something where gravity is something that you need to worry about, or where in a competitive match other robots will be trying to push you around and then you want to stay in one place. But we can get by with brake for this particular program. It shouldn't really make a huge impact on us. And ideally, using hold actually puts more strain on the motors. So it's better when you can try to use brake instead, unless you absolutely have to use hold. So now let's run it again and see if it still does the drifting. I'm hoping it does less drifting. So run it. It still did a little bit of a drift, but not quite as much. Now let's see what happens if we switch it to hold. Maybe this will behave the way we want. Run it again. Ooh, it stopped much sooner that time. Let's run it 3 times. That definitely stopped it much more quickly. It's still drifting, but I think that is more of a result of the simulation than it is of the actual code. So we'll keep it at hold. It seems like that's the most precise. So it actually like stops it really precisely. So we'll use that. Now, we have our basic code. We're telling it to stop with hold. we tell it to spin for 1 second, and then we tell it to stop again. But we need to get to this wall, and then we need to turn. So the basic code for this would be, I mean, the simplest way would be, okay, well, I want to sleep for like 2 seconds. Let's see how far I get with 2 seconds. And you go, okay. You run it again. You say, oh, okay. Well, 2 seconds. Hey, that's perfect. And then you're like, okay, then we stop. And then we sleep for 1 second. And then we make it turn. So we're like, how do we make it turn? Well, we could apply speed in one direction and tell it to go in reverse in the other. So in this case, we'd want our left motor to spin forward and our right motor to spin backward. So we go reverse, and then let's change the speed to 10, and then let's let it sleep for a second. Let's see how much of a spin that gets us. And then we also tell it to stop again, so we copy this code. So now we have, basically we have stop before the wall. And I'm adding comments to help me remember. This is a turn. And then this is a stop after turning. So let's watch this and see if we got it. So we go forward. Oh, what did I do wrong? Oh, I might have to do vex. Click on direction type. Reverse. I guess it doesn't have reverse, even though it has forward. That's really weird. Whatever. Okay. Go forward. Stop. Turn. Not bad. I could tweak it a little bit. Maybe have it maybe be like 11 instead of 10. And maybe have it go forward for 2.25 seconds, and see if that does it. Go forward, turn. Ooh, it lagged that time, so it didn't go as far. Sometimes if the simulation frame rate drops, it won't go as far. Like there, that's better. There. So that's basic code, and using sleep is a way to do it, but it's not the best way, because as you noticed, there was like inconsistency. It sometimes went this far, it sometimes went this far. There is also the problem of, what if Mr. Symbiote decides to move these walls? Well, then suddenly you're not sleeping for long enough, or you're sleeping for too much. So that is a problem. And so in the next video, we're going to talk about how we can solve that problem using a different technique. Even though this is one way that you could drive your robot, it's not super reliable. So let's see if you can think of another method, and then we'll talk about it in the next video. Thanks for watching.